All right, let's talk about Turing machines. So, as I mentioned last time, I'm trying to give you sort of an idea of the historical environment which produced the idea of the Turing machine. This is all like early 1900s. I mean, like the first decade of the 1900s. This whole like line of thought can be summarized by some very deep questions that were asked by Hilbert in the year 1900. Actually, there was like there was an international meeting of the world's mathematicians in the year 1900, where part of their agenda for this meeting was to kind of set the tone for the coming century, and propose. And Hilbert was one of the sort of leaders of this group, and he proposed specific questions. I don't remember how many. This is around 20 different specific unsolved math problems that he believed would work on these problems, would push the subject through the 20th century. And to a large extent, he was correct about these Hilbert problems. They are now known as the Hilbert problems, and it was like for much of the 20th century, people were working on them, and as they were solved one by one, they made people famous. Some of them are not solved yet. One of them was the Riemann hypothesis, which is now still unsolved. That's a major problem in number theory. Another one is the continuum hypothesis, which has now been proven to be undecidable. This is something that I mentioned last time, that there are some mathematical statements. Of course, there are mathematical statements which you can prove because they're true. There are ones that you can disprove because they're false. But there's actually some statements which cannot be proven and also cannot be disproven, and those are called undecidable propositions. And at this point in history, they didn't realize that this was the case, but now we understand. And actually, this is true of modern mathematics. Like, if somebody has a theorem that they're trying to prove, it used to be that there were only two options. It was either true or false. Now we understand that actually there are three options. A theorem can be true and you can prove it, or it can be false and you can prove that it's false, or it could be what we call undecidable, which means it can't be proven to be true or false. Anyway, here's a question. So one big question that Hilbert had was Hilbert's question of are all mathematical statements provable or disprovable? Right? And the answer is no, although I think at this point in history, probably the opinion of general people was probably yes. I mean, I think throughout the history of mathematics, for most of time, people have more or less believed that every mathematical thing you could, in theory, you could prove it or prove that it's false. And certainly if you ask ordinary people in real life today, probably the impression that most people have about mathematics is that all of mathematics in principle it can be proved or disproved. But actually it's not true. Anyway, the answer here is no. There's a related question that Hilbert was asking around the same time, and this is what directly led to Turing's work. A related question, this one I think to most people sounds like a stupid question or a question which is sort of hoping for too much. But Hilbert had this question, is there or can there be some kind of a master procedure for deciding, well, maybe instead of saying deciding, is there a master procedure for proving things? The idea here is, of course, we, even kids these days, understand that for certain types of mathematical problems, there's like a way to do it, right? And there's like a specific formula that you need to use or a specific method that you need to apply. And then once you know the formula, no matter like what your teacher asks you, you can plug it into the formula and figure it out. Hilbert's question is about something like, is there some kind of big formula that you can use to prove things, just like anything? Is there some kind of master procedure that you could use to prove any theorem? I think if you ask people, what are your thoughts about this? Do you think the answer is yes or no? Is there some kind of one single, like it may be extremely complicated, but one single method which you could use to logically prove anything? I'm seeing people say this. I would say I would guess that the impression of most people is probably that's not possible. And I would say if the answer were yes, this would basically be the end of like mathematical research as a creative endeavor. It would mean that if you ever wanted to know if a theorem was true or false, you just sort of like plug it into this machine and it will tell you the answer. And it means that there is no longer, like we as serious mathematicians like to feel like when I prove something, I am exercising my own creativity and I am having like some sort of like a leap of intellect in my mind when I finally figure something out, all right? And these are things that are not the result of me just doing some kind of standard procedure over and over again, but it is somehow a real creative effort. So anyway, this is Hilbert's other question about these things. Again, we now know the answer is no, but this was not understood at that time. If there were some kind of master procedure for proving everything, then basically all mathematicians would stop whatever they're doing, learn that procedure, and then apply that to everything. And then you wouldn't have to learn anything else ever in mathematics other than this single master procedure for proving theorems. All right. The answer we now understand is no, but it wasn't known back then. This specific question, though, caused people to start thinking very seriously about that. Procedure, specifically, what counts as a procedure? All right. They didn't use this word at the time. This word did exist at the time, but they didn't use it in this way. A more modern way of phrasing this question is what counts as an algorithm? This is the word that we use nowadays. Usually in common parlance nowadays, the word algorithm just means a computer program, but more generally it means any kind of specific procedure for doing something. And if you want to, like this, the answer to this question that Hilbert was asking is no, but if you want to prove that the answer is no, you have to have a specific idea in mind about what exactly counts as one of these procedures or what does not count. And there were actually more than one people who tried to give an answer to this question, what should count as a procedure. And there was one that I'll mention that we're not going to talk much about. This guy named Alonzo Church. He tried to view this kind of procedure in terms of, so his idea was procedures are things which can be expressed. This is kind of like, I would say this idea is this would naturally occur to any maybe like high school math student. They would say something like procedures are things which can be expressed by equations. So when Hilbert was asking something like, is there a master procedure? What Church had in mind was some kind of big, complicated formula that you could plug stuff into and get an answer out of, all right? Things that can be expressed by equations. Now, not every equation is well formed, so Church actually created a very specific theory of what kinds of equations he was talking about, and he called this led to a body of ideas that we now refer to as the lambda calculus. The lambda calculus is still kind of important, a big deal. I'm not an expert in the lambda calculus, but there are a lot of people out there who really who really like the lambda calculus. Maybe if you know Python, there's something in Python called lambda. Have you used lambda in Python? I don't see. I use lambda ever so often in Python. Anyway, that is called lambda. It's inspired by the lambda calculus. Anyway, the other person with the major idea about this was our buddy Alan Turing, and his idea was procedures. This, you could say, is very much an idea born of this time in history. Procedures are things which can be built as machines. This, of course, is like the age of industrialism, and especially kind of the rise of machines in warfare. Turing was sort of a child of the two world wars, and machines were a big deal. And calculating machines were becoming popular in real life, although they were very specific purpose. There was like a machine for adding or machines for multiplying. No general purpose computing machines, but specific purpose calculating machines. And anyway, just the same way that like Church was talking about equations, and he had to describe very specifically what kinds of equations he was thinking about and how you could translate any procedure into one of these equations called the lambda calculus. Turing, in the same way, had in mind a specific kind of machine that he believed could calculate any procedure, and this is what we now call the Turing machine. Turing referred to this as, he called it the universal machine. And this was obviously a truly important idea, and this idea really set the stage for the technological development of the entire 20th century. But Turing's idea was that there could be a type of machine which did not have a specific purpose, and it did not have a specific task, but there could be a type of machine whose purpose was that it could, in theory, do anything. And so this is Turing's concept of the universal machine. So we are going to discuss what exactly are the capabilities of this universal machine that Turing described. He was not, at this time, he was not trying to engineer a particular machine that he could actually build, and Turing himself never tried to build a universal machine. It was an abstract idea that he was trying to use in order to answer these questions here. But it turned out, he, at the same time, invented computer science and changed history forever. But let's talk about Turing's universal machine. So we now just call this the Turing machine. And Turing described it abstractly, kind of like a NFA or a DFA. And in fact, the NFA, DFA, that didn't exist. Turing invented the Turing machine, and this was the first idea of its type. And then later on in history, people said, what if we made like a Turing machine but stupider? And they called that the NFA and the DFA and the stack machine. They are meant to be stupider variations of the Turing machine. But the Turing machine was kind of the OG and also the most complicated of them. It's more complicated than the others. Anyway, the Turing machine, I will tell you sort of what it does, what it has. Just like a stack machine or an NFA, it has certain things. First of all, it has states, right? So it looks like, we are going to say on your homework or whatever, you're going to draw me little Turing machine diagrams. It has states. So the Turing machine, I'm just going to write TM all the time for Turing machine. It has finitely many states. And we are going to draw a diagram for them that looks, the red cross. They're on me. I got that sweet blood. They call me often to get me to make appointments. The Turing machine has finitely many states. And we are going to write sort of state diagrams for Turing machines with, the circles and the arrows. So they look kind of like NFAs. The transition arrows will be labeled in a slightly different way. It also has a separate kind of memory thing, but it's more sophisticated than a stack. A stack, of course, you can only use, the thing on top. So the Turing machine has finitely many states and also has, this is how Turing described it originally, the tape. The tape is tape, not as in like adhesive tape, but a long sort of, you imagine like a long strip of paper. The tape looks like this, and it's sort of divided into little bitty bits. And on the tape are written letters. In our case, we're usually going to use, A's and B's as we usually do in this class. So it has the tape, and the tape has letters written on it. All right? The tape is infinitely long in both directions, okay? You cannot create a Turing machine in real life because of this, although our real life computers are basically like Turing machines with super, super long tapes, although technically not infinitely long. Anyway, it has the tape with letters. So the tape is infinite in length in both directions. And the tape, each little spot of the tape can either have a letter on it or it can be blank. And just because it will become helpful for us, we're going to actually write the blanks as a big B. So when we're doing Turing machines, just because sometimes you want to write a blank, and if you just leave it as a blank, you won't have anything to write. So we use the big B. Some books use the epsilon for obvious reasons to indicate sort of a part of the tape which has nothing on it, but we're going to use the big B. All right, the tape is infinite in both directions, and the machine has what is called the head. So the Turing machine has a head, and the head you should imagine as like a little gadget that moves back and forth along the tape. And the head, so I will say in each step of the calculation, and like when you're looking at one of these diagrams, it's basically like every time you follow one of the arrows is one step of the computation. And in each step, the head has a location along the tape. And sometimes it's indicated like this, that little hat there. That means the head is right here looking at the A. And the head can move back and forth to look at different portions of the tape, all right? And in each step, the head reads the tape wherever it is. It has a particular location along the tape, and it can read one letter at a time. So the head reads one letter from the tape. Of course, it might be blank. Depending on the state of the machine, the head will decide what to do. And what it's allowed to do is, in each step, the head can change what it sees on the tape. So the head reads one letter from the tape, then writes one letter in that location, replacing what used to be there. So the head will see this A and then maybe change it to a B, or maybe keep it as a A. The way we represent that is we see a A and change it to a A. So you can change it to what it was before, and that will accomplish just keeping it. And then, lastly, moves to the right or to the left by one spot. These are the capabilities of the machine. All right. Just, I like to think sometimes about, like, people say that Alan Turing was some kind of super genius, and some people say he was like the biggest genius of the 20th century or something. I think well, without a doubt, I don't know, I'm not a historian, but I would say he's certainly the most influential mathematician of the 20th century in terms of impacting the real world and how we do things. He, as a purely abstract mathematician, really sort of had immense impact on the world. But this, in my opinion, is a truly ridiculous idea to come up with this whole thing as an answer to this question: is there a master procedure for proving things? And then some guy, Turing, is like, okay, hear me out. I got a tape and a head, and it moves back and forth. Like, I immediately think, like, did you even hear the question I was asking? Why are you talking about this at all? And the answer, of course, is like, okay, if you want to make sense of what procedure means, you have to imagine any procedure is like an algorithm. That is to say, it's something which can be accomplished by a machine. And then I would say, what kind of a machine you're talking about? And he'd be like, I'm talking about the tape and the head and all of that. This, to me, is a ridiculous idea, but it's such a good idea also. Nobody actually wanted to make this machine, but people, as soon as Turing had this idea and it became well known, people started thinking about, okay, how could we actually make a real machine that acted like this? And they started to have ideas about something like some kind of electronic memory bank and a central processing unit which modifies values in that memory bank. And that's how we have like real life computers that we have now. All right, anyway, let's just talk about an example. Yeah, we gotta go soon. We got 5 minutes. I can draw an example here though. Maybe we'll talk in more detail about this next time. Here is an example of a Turing machine. It has 4 states, and I'm gonna give them names. We don't always give them names, but for the sake of talking about this example, it'll probably be a good idea. It has an accepting state and a starting state, just like an NFA diagram does. All right, and it has arrows, and I will draw some of the arrows here. So what you see on the arrows are more complicated than just NFA arrows. Each arrow has a thing, and then a slash, and then another thing, and then a comma, and then, in this example, a R. Those like 3 things which are labeled on each arrow are describing these 3 things that the machine does. It reads a letter, it writes a letter, and then it moves. All right, so when you see this AAR, it means read A, write A, which is to say you just leave the A like it was, and then move to the right. This R means to the right. Sometimes you will see a L there, which means move to the left. All right, let me write the rest of the arrows in this example, and then we'll talk about it. Oops. CCR. Here's another CCR. I got a loop CCR here. Here I have blank blank R. This is why we, in this section, we want to have a special letter which represents the blank, because sometimes the head will move itself sort of all the way out until the head sees a blank, and that's okay. It just has to know what to do at that point. And I have one more arrow from the T state. Sorry, I have to go around the bend here. This is also a blank blank R. All right, so this is a very simple Turing machine which always moves to the right. You can see I'm only using R's, there's no L's here. So in this example, the head is only moving to the right. And also in this example, the thing that it reads is always the same as the thing that it writes. But I will say in general, sort of, if you see X/Y, R, this means read X, write Y, move to the right. All right. And if you want to read the X and leave it as an X, you just write X/X, R. If you want to move to the right. All right. Let's just try one string and see if it's accepted. So just like NFA, DFA, or whatever, these things accept or reject some strings. Let me tell you what it means to be accepted. We say a string is accepted if the Turing machine ever enters an accepting state, which in our example is there is one accepting state. If the Turing machine ever enters an accepting state, starting with the string on the tape. All right? That's what counts as accepted. Let's just try one example. So in our case, I would like to know, is AABC accepted? All right? So the idea is the machine begins with that on the tape. So the tape, I'm just going to sort of write, I'm going to write several times. What do you see on the tape? You begin with the tape in this configuration, and we should also indicate where is the head. In this case, the head, when we begin, the head starts all the way on the left end of the tape. It is here, and I'm going to put a little S there to indicate that the head is now pointing at the first A, and we begin in state S on the diagram. So when you're sort of doing the Turing machine computation, you have to keep track of, you have to be sort of looking at the diagram and also keeping track of what happens on the tape. All right? So that's the first step. What's next? So you look in the diagram, it says in state S, if I read an A, it should do this arrow. And I am looking at an A on the tape right now. And this arrow means replace what was an A on the tape, keep it an A, and then move to the right, and stay in state S. So the next version of this is that. Sorry, I meant to put an S here. Like that, all right? The first A there stayed as an A, and then the head moved to the right, and the head is still in state S because that arrow on the diagram is a loop back to S. All right, and let's follow the rest of the arrows. So my next arrow from S, I am reading A again. I'm actually going to do the same thing. It will stay in state S and move to the right by one position. So now it will say A, A, B, C, still in state S, looking at the B. All right. Next on the diagram, in state S, when I read B, I have to follow this arrow. And so the B will stay like it is. It will move to the right and now be in state T. So it now says A, B, C. There. The head moved to the right by one position and changed to state T. What's next? In state T, I am looking at a C. So from this state, looking at reading a C, I go here. I go to state R and move to the right again. We're almost done here. Sorry, I'm over by a minute or so. A, B, C. I'm going to write the blank here just because I usually don't write the blanks unless I have to write the blanks. Really, in reality, there are infinitely many blanks stretching out forever in either direction. But I'll only write them if they become necessary. Okay, now I'm in state R, looking at the blank. That's this arrow, BBR from state R. I'm reading a blank, so it should stay as a blank. The head should move to the right again by one position and move into state Q. So actually this sort of goes even further down into the blanks. It's over here now in state Q, all right? And what I said up here was the string is accepted if the Turing machine ever enters an accepting state. Q is an accepting state, and so we stop and this string is accepted. So Q is accepting. So it's over. And the string is accepted. The Turing machine always just keeps on going until it gets to one of the accepting states or until it gets stuck. Sometimes like there's just no arrow that's appropriate for what it's looking at. Yeah.
So is it like a DFA where, or like an NFA where if it reads like something it doesn't have an arrow for it breaks? Or
That's right.
okay.
Yeah, but unlike an NFA, it's not allowed to have, say, 2 outgoing A read arrows. Yeah. Yeah, we'll do a bunch more examples next time. Thank you for your attention. Have a good weekend.